Um, Let me start with the motivation. So there are very many very large graphs in the world, internet, brain, and so on. We listed here some. These are very large graphs or very large networks, if you wish. And in fact, in the sciences, including social sciences, this notion of that a structure is a network or has an underlying network is becoming more and more common. Probably physics started this with Ising model and things like that, but it's becoming more and more widespread. So these are really very large networks. Now let me do a little quiz. Would you like to know whether the internet has an even or odd number of nodes? Let me remind you, those who ever took a graph theory textbook, opened it, would see that whether a graph has an even or odd number of nodes occurs as a condition in one of the first theorems that the book will ever present. If a graph has an odd number of nodes, then it must have a node with even degree. That's one of the very basic, simple results in graph theory. So this question from classical point of view is a very natural and obvious question, but of course meaningless for the internet. On the other hand, if we ask what is the average degree, so for example, look at the network of all people in the world, and edge means that they know each other or regularly meet or something like that, then it makes sense. How many, an average person, how many other persons does this average person meet? That's a meaningful question. Of course, it changes a little bit day by day. New people are born and people die and people change, move and so on. But sort of globally, it's a meaningful question. Here is a tricky one. Is it connected? Let's think again about the internet. Is the internet connected? Well, I think the answer is an obvious no. I mean, I don't know if I am on a plane, then whether my smartphone, it's not connected, so is it a kind of isolated node of the internet? But sometimes, of course, a router breaks down and maybe a whole house or a whole office remains without internet connection. But that's not really what we should mean by connected in these large-scale graphs. If, say, all connections between continents are cut for, I don't know, by earthquake or accident or something, then I would say that the internet is not connected. And that actually happened maybe 20 years ago when Africa was cut off the rest of the world for a week or something like that. There was no internet connection there. So this means that even the definition of connected should be more carefully thought through if we want to talk about very large graphs. Here is I will come back to this example repeatedly. Find a maximum cut. So a maximum cut means that you would like to split the points into two parts so as to maximize the number of edges that goes across. That's a very important problem. I will come back to it. Here, what I would like to point out is that the answer to this question is already not clear what we mean. I mean, do we want to really get two lists of all, say, people in the world who are by name, who are on one side and the other side of this maximum cut? It's not, I mean, maybe they are men and women, but there could be many other cuts, and it's not clear what the answer. How can you answer such a question or about the internet? You want to list all the devices on one side and all the other devices on the other side. That would be stupid. So it's not clear that this question has a meaning. I will come back to this. So the basic setup is that the graph we want to study is huge. It's not known explicitly, not even the number of nodes. And here you could, of course, in most cases know approximately the number of nodes, but I will idealize, and I will assume that I don't know anything about the number of nodes. So what is the minimum amount of information that gives me meaningful results about these graphs? The answer is different in two extreme cases, and we don't really know many other cases which are neither dense nor very sparse. But the easy case is the dense case. That's what's best understood. Here, the idea is that the way to get information about this huge graph is to sample uniformly a bounded number of times, and a node a bounded number of times, and then just look at the edges between these nodes. So take a random subgraph. It's like
what's the word uniform?
Uniformly means that every node has the same chance of being picked. I'm not saying that this is a very easily done thing, but I mean, that part in itself, I mean, statisticians have ways of selecting a random member of the society and somehow make sure that the distribution is as close to uniform as possible.
Random.
Sorry?
Uniformly random. That would make it clear.
Okay, so uniformly random node. In the bounded degree case, that would not say much, because you have a graph which is very sparse. If you take out 100 nodes, most likely you don't see any edge between them. So here we have to allow a little bit more. So we can sample one or possibly several random nodes, and you can explore the neighborhood, because luckily the degrees are bounded. So you can explore the neighborhood in bounded time, and you explore it to a bounded depth. And so you see, again, some information, some subgraph of the whole graph this way. And this area was developed. It's called property testing, and there are many people have made some very important contributions to this. And I probably have not listed all, but anyway, I just wanted to mention that in computer science, this kind of question has been studied a lot. Of course, usually in a more finite. So I am talking about the extreme where I don't even know how many nodes there are. So, and then there is, of course, a question of whether you can get some global information. But I will not go into that. That leads to interesting questions. Now, everybody knows now more about networks, because we have been through this pandemic and we are reading about various things that are being done. So contact search is almost the same as this bounded degree except it's limited to those people who are known to be ill. And then you do a contact search. It means explore a neighborhood of that person in the network, social network of people. And then there's also global information there, daily data that you read from the newspaper or get from hospitals and so on. So definitely this COVID gives a little bit more feeling of what should be done. But I am in this very simple, mathematically clean two ways of obtaining information. Now, let's go back to the question, what kind of question do we want to know? One is, the simplest one is that we want to estimate some parameter of this network. So, for example, in the dense case, you want to know the density of edges, what fraction of all pairs are connected. Or you want to know the density of triangles, what fraction of triples form a triangle. Or you want to find the size of the maximum cut. It's another question, how do you actually know the cut itself, but you just want to know what fraction of the edges is picked up by this maximum cut. Now, there's a more difficult issue is property testing. So in this case, you want to know some property of the graph. Is the graph bipartite? Is it triangle-free? Or is it perfect? Never mind if you don't know what a perfect graph is. It's some nice class of graphs that people love to study. Or is it planar? Can it be drawn in the plane without crossing? How do you test this? Now, in this case, again, it's not even clear what the right question is. If you want to know, for example, whether the graph is triangle-free, well, maybe it is triangle-free, it's a huge graph, but somewhere in the middle of China, there is a single triangle. If you do random sampling, you will never discover this. So, of course, if you sample and see that that in the sample you took there is a triangle, then you can be sure that it's not triangle-free. But just from the fact that you don't see any triangle at random spot checks, it doesn't mean that it's triangle-free. We'll see that this is actually a very deep question. What does it mean to test for triangle-freeness? And then, as I mentioned about the maximum cut, you want to compute a structure, a maximum cut, you want to find a maximum matching, you want to find the summary irregularity partition or anything like that in the graph. These are global structures in the graph, so what does it mean you want to find them? It's a difficult question in itself. So let me introduce this maximum cut problem. So again, you want to split the points into two classes so that you maximize the number of edges between the two classes. And for good measure, you divide by n squared so that you get a number between 0 and 1. And it turns out this has many applications. But what is more interesting is that it's one of the most beautiful examples that has been solved essentially in the theory of approximation algorithms. It was shown that to find the maximum cut is NP-hard. That has been known for a long time. What is interesting that it's NP-hard even if you allow a little error, 6% error. It's still NP-hard. And that was, sorry?
What does it mean to allow an error? 6%?
It means that you find a cut. This is still in the classical case, so you actually find the cut itself. And you don't have to find the absolute maximum. If you get within 6% to the absolute maximum, then that's fine. It's a usual setup for approximation algorithms. And it's still hard if you want to get within 6%, but if...
Like 1/16 of the maximum.
Yeah. So you want to get to the maximum, and you want to find something which is only 6% off the maximum. So you find something which has fewer edges, but not too few. But there is a polynomial time algorithm which computes it about 13%, with about 13% error. So it's quite interesting that this is complexity theory. So there's no polynomial time algorithm can compute it within 6%, and there is a polynomial time algorithm that computes it with 13%. In fact, that was proved in the early 90s.
What does that one mean? That error, what does that mean? Compute it within 13%?
So it means that it computes a cut that is always at most 13% worse than the maximum. And the 13 is not exact, but there is some well-defined irrational number which gives the instead of the 13. And the point is that since then there is this. I mean, NP hard means that if P is not equal to NP, then there is no polynomial time algorithm, and there is another. Somewhat stronger assumption. It's called the unique game conjecture, and Subhash got the Fields Medal for this. He's not here, but he was on the Abel committee. So anyway, based on his work, we now know that the 13% is that number is exact. So. But it's based on a stronger assumption than P not equal to stronger complexity assumption. Anyway, so this problem is very interesting from the complexity point of view. Both sides are non-trivial. But I would like to talk now about our model. So here, if you see, this kind of thing is supposed to symbolize a graph where you don't really know what's inside. Can you see it? Yeah, it's just a sort of gray area there. Doesn't mean. So now suppose there is a cut. That's really a cut with many edges, probably the maximum cut, but it is a cut which contains many edges. Now you take a sample. And this is in the dense setup, so you take a sample, and you randomly choose these red nodes, and you count the number of edges. And inside this graph, this is now a finite graph, there is a cut, and that has a certain density. And the question is, how does it relate to the density of the whole thing? It's very easy to see that if, say, 20% of all possible pairs go across in the big graph, then on average 20% will go across in this sample too. So that is the easy part. The difficult part is if the converse, which is also true. So it's true that if you sample enough nodes and the density of the maximum cut in each of these induced subgraphs will be close to the density of the maximum cut in the whole graph, no, then it will be close to the max cut in the whole graph with high probability. The direction that it cannot be that the sample will have at least as many edges, at least as dense as in the big graph. That's easy, that's just law of large numbers. But the reverse is The converse is more difficult. So suppose that no matter where I pick a small graph, I find a large cut in that. Why should these line up to give a single cut through the big graph? And in fact, originally there were very complicated proofs of this fact, but now we will see that in fact graph limit theory provides a nice way of handling this. So f is a graph parameter, say values between 0 and 1. Graph parameter means some number that you assign to every graph, like the density of the maximum cut or the density of edges or whatever. Then the theorem we have is that says that such a bounded graph parameter can be estimated in this way, so taking samples and computing an estimate of this from the sample, if and only if on every convergent graph sequence it evaluates to a convergent number sequence. So a convergent graph sequence in the sense that was introduced in the previous talk. So a trivial example is a graph parameter. So f is now fixed, say f is a pentagon, and you want to know the pentagon, the density of pentagons in the graph G, then by the definition of convergence, it satisfies this, so therefore it's estimable from samples, that's a triviality, of course. It's essentially the same property, but has a nicer reformulation, or more analytic reformulation, that you can go to this completion space, this W0, consisting of all graphons, or these functions, and you can extend the value to a function on this space, and that should be continuous. So if you can extend it to a continuous function on this space, then it can be computed from samples. By the way, this W0 is this completion, and I think it was not mentioned in the previous talk that this is a compact space, which means that every such estimable graph parameter, for example, has a maximum, has some graphon on which it's maximized or minimized. So it's an absolutely useful property of this thing. Parentheses, this is essentially equivalent to Semiredes regularity lemma if you are, but I will give other equivalents of Semiredes regularity lemma a bit later. So
compact space follows from Semiredes lemma? That's just
I would say yes. I mean, you have to work a little, but Semiredes lemma is the key to the proof of the compactness of this space. Well, really, Semiredes lemma is behind the equivalence that was in my first proof of the two definitions of convergence. From the original definition, this compactness is easy because you can just, for every sequence of graphs, you can pick a convergent subsequence just by diagonalization. So it's a very routine argument. To prove the converse, you need Semiredes regularity lemma. Now, how about the density of maximum cut? This doesn't help us with it because it's just some kind of abstract nonsense. But there is let me just formulate for you a finite theorem, which again characterizes these parameters that can be estimated. And there are three simple conditions. One says that if you delete a node from a graph, for a large enough graph, then the parameter doesn't change much. This obviously has to be. The other one is this GK are these blown up graphs that Kati introduced. So you replace each point by K points, blow them up by K twins. And that gives you a sequence if you grow it more and more up, and it should be convergent on this sequence. These are AND. So these three conditions have to be satisfied. And the third one is that this is basically the maximum cut. Okay, so maybe, so this is that every node blow up, and this is actually this cut distance between the two graphs on the same set of nodes, and it says that if the cut distance is small, then this parameter should change little. And these are almost trivial to verify, actually trivial to verify for the density of the maximum cut. So this is a general theorem from which it's basically all the, so it settles this question as far as I can see, what parameters can be estimated. Now let's go on to this property testing. So first I would like to define it exactly. So we have a graph property, I note it here by P. Now it is testable, it's called testable, if there is a test that you perform on the samples. And the test gives yes or no for the sample, which means it's some property of the sample. And the first condition is that if the graph does have the property, then the sample should be accepted. So then the sample should say that yes, it passes the test. And then the second one is a little bit more complicated. First of all, we have to look at big enough tests, and there is an epsilon. And if the graph is far from having the property, and here the distance is not the same distance as before. This is how many edges you have to change in the graph to get a graph with that property. It's called the edit distance. So you have a graph, and you want to say that it approximately has the property because I only have to change 1/1,000,000th of the edges, and then I get a graph with the right property. So it's very close to a graph with the property. Then the large enough sample should fail the test with high probability, probability at least 2/3. So basically we can either conclude that the graph has, we can say that the graph, if the graph has the property, then we will say that it has the property. And if it does not have the property, then we may not recognize this, but if it's far from the property, then the test should show this. And this is a much studied question. Let me get to this triangle-free graphs, which is really an interesting case. So suppose you want to test whether a graph has, how much time do I have?
You have about 20.
Oh, okay. Oh, great, thank you. So I'm not, okay, so then I go through this triangle-free thing. So I sample, so I have a big graph. I want to know whether it's triangle-free. I take a sample, which is I denote by G prime, say on 100 nodes, and I look at this G prime. If I see a triangle in this G prime, then of course the graph G has a triangle. If I don't see a triangle in this sample, then I, of course, cannot conclude that the graph has no triangle, but we can conclude that it has only a few triangles, because if it had, say, large fraction of triples would be triangles, then my random sample would pick some of these. So if I don't see a triangle, I can conclude that the triangle density is very low. Basically less than delta times n cubed triangles for every delta. And now it turns out that there is, but that's not what I want actually. I said that I have to show that G is close to a triangle-free graph. So the question is, having few triangles, does it mean that the graph is close to a triangle-free graph? Now, close means that I can change a small fraction of edges, epsilon times n squared edges. But there are constant times n cubed triangles, so it's not that I delete an edge from every triangle. That I cannot afford. So the question is, suppose that the density of triangles is small, can I delete a small fraction of edges to get a triangle-free graph? And that's a famous result by Ruja and Semeredi. It's called the removal lemma. And it has some very important applications in number theory, which I will not go into, but it was a very important step. And it's not an easy lemma. So you see there is an epsilon and a delta, so the delta depends on the epsilon. Now the delta, the way the delta, you would think that the delta is maybe epsilon squared or something like that. No. Delta, at least the best delta we know now, is like 2 to the 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 1 over that, of course, delta is small. And the height of this tower is the log of 1 over epsilon. So delta depends in a very bad way on epsilon, showing that this is not a trivial fact that you can do this.
That shows the proof is complicated, but not that it's not a non-trivial fact.
Okay. Yeah. Now, again, the more general, the better. Alon and Shapira proved a very general theorem about this. So every hereditary graph property is testable. So what does hereditary means? It means it's a property that's inherited to induced subgraphs. So if the graph has this property, then delete any subset of the nodes and it still has this property. So triangle-free is a trivial example of such a property, but there are many. Bipartite is another property that has the planarity and many other hereditary properties. And every such graph property is testable, was proved by Alon and Shapira. That's an amazingly general result, and so bipartite, triangle-free, and if anybody knows what a perfect graph is, then this is a very surprising fact that perfect graphs also are testable, because this is a non-trivial class of graphs. So, it's not even known, well, it was proved much later, that said it's a very complicated algorithm to test a graph for perfectness in polynomial time. So that was a very difficult question, and it was only proved solved by Simon Robertson and others much more recently than this result, which is, of course, in another model. Now, let me get to something. So these testable graph properties, these are a little bit like P. So they are the nice ones. These are which we can handle. And there is NP. So what is NP in this setting? So suppose you want to know, for example, whether a graph can be colored by 3 colors. That's a hereditary property, by the way, so it's testable. Now, but it's much easier to test if you have some outside help. That is like Merlin that Avi was talking yesterday. Somebody who can do arbitrary large computations in his head in a second, and then he looks at this graph and gives you a 3 coloring of the graph. Then all you have to do is to take a random sample and see that this is well colored. Then you can conclude that, well, the coloring may not be, well, by coloring I always mean, and in graph theory we always require that we consider those colorings where the condition is that an edge, 2 endpoints of an edge must be colored by different colors. So you test. Now maybe there is somewhere a bad edge, but that will be a small fraction of the edges if your random sample doesn't pick it up. So it helps. And now to give you a proper definition, we look at a graph and we make it a little bit richer. We may direct the edges, or we may color the edges, or if you want, you can color the nodes. So you sort of decorate the graph in some way. And then I call the shadow of this decorated graph, if you forget the orientation, delete some or maybe all colors, forget the coloring, in other words. And now suppose that there is a property of directed colored graphs, then the shadow of this is the shadow of the property is just the shadows of graphs with this property. So if I am interested in 3 colorable graphs, then I look at the decorated graphs which have nodes colored by 3 colors, and then the shadow of that class is my 3 colorable graphs. And so we say that a property is non-deterministically testable if it's the shadow of a testable property of these kind of color-directed graphs, where for these the testability is defined exactly as either has the property, then the test has to accept it, or if it does not have the, if it's far from the property, then the test should discover that it's far from the property. So this is a non-deterministically testable, the notion of that. So, for example, the question that a graph is 3 colorable is non-deterministically testable because Merlin comes and gives us the 3 colors, and then we pick the random sample and see that there the coloring is okay. Let me remark that it's not obvious at all that 3 colorability without this Merlin's help is testable. I mean, you take a subgraph. Of course, it has to be 3 colorable. It's an NP hard property to test, but it's still finite, so you test the subgraph, whether it's 3 colorable. But then what? You only get that most subgraphs are 3 colorable of, say, 100 nodes. So why is it that all these 3 colorings fit together to give a single 3 coloring of the whole graph? It's the same kind of problem as for maximum cuts. So here are some examples. So for example, the property that the graph contains a huge clique containing third of the nodes is non-deterministically testable because Merlin comes and circles for you the nodes which are in the clique. And then you just have to check two things. First of all, that the circle nodes form a clique, and second, that the number is at least third of all. And both of them are easily tested. It's a random test will.
Is a full subgraph? What is a clique?
Oh, a clique is a complete subgraph. So whether it has 1/3 of its nodes that any two of them are connected. It's a property you may want to know. And if you pick, so again, with Merlin's help, it's easy to check. Without Merlin's help, it's not clear. And so here is this theorem that I wanted to show you is that actually, if it's non-deterministically testable, then it's testable. So Merlin's help is not needed. Okay, so in a sense, this says that P is equal to NP for property testing among dense graphs. So non-deterministic help does not help. And of course, we believe in other situations it does. So just an interesting example for where showing that this P is not equal to NP problem is not sort of obvious. In other settings, it does not hold. And the proof, which I will very briefly sketch for you, grows by graph limit theory. And since it goes through infinite objects, this is a pure existence proof of an algorithm, which is a strange notion. So you prove that there is an algorithm for something without giving the algorithm. So how does graph limit theory come in here? So this is, what is this? So there is this property A that we want to test. And suppose it's not testable. What does it mean it's not testable? It means that there are graphs, larger and larger graphs, which are in this property, have this property. And there are other graphs, these are the Fs, which are far from having this property, but they cannot be distinguished by tests. What does it mean it cannot be distinguished by tests? It means that for every graph F, the density of F in the G's and the F's has the same limit. So if there are infinitely many F's, sorry? So what it means, what kind of, a test really mean that, or it's equivalent to saying, sorry? Yeah, so it's unfortunate I denoted these by F's. So suppose so I want to take the density of graph L, that's the small graph, and I determine the density of its density in the G's and the F's, and they must have the same limit. Because if they don't, then that means that there will be, that the density of this particular small graph L will distinguish, it has to accept these, and it will reject these. Because testing this L, I see that it's not what it should be for the real good guys here. So, okay, I'm going on. So,
what does that mean?
so that means that it's not a testable property. So there are graphs which have the property. There are graphs which are far from the property in the sense of you have to change many edges to restore the property. And nevertheless, they cannot be distinguished by sampling. That means that this property cannot be checked by sampling.
You have the words you said and you have the picture. I didn't connect the picture and the words.
Okay, so the middle part I will explain in a minute. So far I'm only explaining that there is this sequence of graphs which have the property, and there is another sequence of graphs which are far from the property. But you cannot distinguish between them. So if you cannot determine this property, I mean, it's a little argument you need here. So if you cannot test this property, then for every L, every small graph L, there should be a graph which has this property and another graph which is far from this property, which gives the same density of this L. Okay. Otherwise, this L would distinguish between the two. And now, so this is a countable sequence of graphs, and this is also, and now we can go to a subsequence because of compactness, and they both tend to the same limit. So this is a graphon here, which is the common limit of these two convergent sequences. This is so far just translating the definitions, which are sometimes a little bit hairy. Now, this is testable. So these graphs are, on the left-hand side, are shadows of these kind of more decorated graphs, which are, have this testable property B. So this is non-deterministically testable, means that they are shadows of graphs in this with this testable property B. Now again, by going to a convergent subsequence of some compactness arguments, these go to a decorated version of this graphon. So instead of coloring the edges, you can also get limits of colored edges and so on. It's all you can imagine. So if half of the edges are colored red and half of the edges are colored blue, then you basically take separately and you will have two functions. One is the limit of the red subgraph and the other one is the limit of the blue subgraph. So in the middle you have a kind of decorated graphon which represents this limit. Now the technical step, okay, and this is the shadow of that graphon. Now there's a technical step here which says that since these graphs tend to here, you can sort of pull back the decoration of the graphon to these Fs. There you have to do some analysis to show that, analysis in the meaning of epsilon deltas, to show that that decoration of the graphon can be pulled back to this finite sequence which converges to it. And that these are J's. But these J's converge to the same graphon as the H's. So it follows that they cannot be distinguished from the H's, which or less and less, so which means that they are closer and closer to having this property B. But B is and their shadow is this, these F's, so it follows that these F's are also close to this B, and then the shadow of B is close to A, contradiction with the assumption that these are far from A. Okay, so this is kind of argument. The crucial thing is that you somehow manage to get to the limit space, and it turns out that in the limit space both halves behave in the same way. So this is what I meant by a pure existence proof of an algorithm. And I have to remark that since then, Gish-Boliner and Shapira actually came up with an effective proof using the regularity lemma. Effective, I don't mean efficient. So there is still this tower dependence of the parameters on each other, but at least it's all finite. Let me come to the third question here, or was it fourth? Third. Computing a structure. And so we would like to find what I could call a kind of representative set of nodes. The set should be of bounded size, and it should be the case that every node is similar to one of the nodes on this set. So what does it mean that two nodes in a graph are similar? There are many ways of defining it. For example, we could say that they are neighbors, or they have the same neighborhood. But these don't work. There is a somewhat, how much time? 0?
I see round up in 5 minutes. It's fine. We have a coffee break afterwards, but yes.
Yeah, so okay. So anyway, let me skip. So you can define a distance of two nodes, which expresses that they are similar. And a representative set is a set where any two nodes in this similarity distance are far, but every node outside is close. And then one can prove that every graph has a representative set, which depends on this epsilon, reasonable number, reasonably small size. I want to show you, okay, I will skip the explanation of the regularity lemma. And just I want to show you that, so here is this graph, and these black nodes are a representative set. Now, if you have a metric space and a subset of it, a small subset of it, you can construct a Voronoi diagram. And so you can create around each of these nodes the set of those nodes which are closer to this node than to any other one. And it turns out that this Voronoi diagram is just the regularity partition of Semeredi, the so-called weak regularity partition, so one version of the regularity partition. It's other compactness, which is equivalent to the regularity lemma, is that this distance on the graphon will give a compact space. Okay, let me skip the how to get the regularity partition from this. The maximum cut is that because of the set is representative, if you compute the maximum cut on this representative set, then it turns out that no. So okay. So this I want to tell you because it's important. So what do we mean by finding a maximum cut in such a huge graph which covers half of the universe? So what we can do is we offer a service. So you want to know whether you are on the right or the left side of the maximum cut. You come up with a node, that your favorite node, and you want to know where it is. Then you come to me, and I'll tell you on which side this is. And so it's a kind of service, and it's consistent in the sense that if everybody asks, then it gives an approximately maximum cut. And the way to do it is that the way I compute the answer is that there is this representative set, which is bounded size. It has a maximum cut, and if somebody comes with a question, I just find the nearest point in my representative set, so the Voronoi cell, which Voronoi cell it is, and I say that whether it's on the right side, I say you are on the right side. If it's on the left side, you are on the left side. And finally, I just want to say just 2 words about bounded degrees. So recall that in this case, the sampling is a little bit different. Once you sample a point, you can also explore its neighborhood to a bounded depth. And let me show you some examples, bad examples. So let's look at 3 sequences of graphs. Gn is a random 3 regular graph. So easiest to think of, I draw on n points all 3 regular graphs. Say n is even for that, that's better be even for that. So all graphs where all nodes have degree 3, I put them in a big bag and pull out one. And that's a random 3 regular graph. And there's a lot of study going around of what are the properties of these random 3 regular graphs. It's a difficult area. Now I can do the same about 3 regular bipartite graphs. I construct, I mean, it's exactly the same. Take all bipartite 3 regular graphs and pull out one. And Hn is just the union of 2 disjoint 3 regular random bipartite graphs. Not the same one, so this, there are 2 independent copies of this random graph. Now, the point is,
they're disconnected?
They are disconnected, yes. Now, the point is that these graphs have essentially large what we call girth in graph theory. So in other words, they don't contain short cycles. That's not strictly speaking true, but they contain some negligible amount of short cycles. So if you sample randomly a point and explore its neighborhood, you see a tree. So these graphs have very simple structures, but all 3 kinds have this very simple structure. So they are not distinguishable by our sampling algorithms. Nevertheless, they are distinguishable if Merlin helps. Because if Merlin comes in, he can 2-color the bipartite graph, and then it will be distinguishable because he cannot 2-color the true random 3 regular graph, or actually he can 2-color, but there will be a large fraction of the edges which are wrong, and which we will discover if we sample. So he can, and similarly the disconnected one, he can color the two parts by 2 different colors, and then we can see that a random sample will show that there are both colors occur, and you never find an edge which connects 2 different colors. So these are properties which are non-deterministically testable, but deterministically not testable. So in this setting, P is not equal to NP. So for the bounded degree graphs, P is not equal to NP. For Nernst graphs, P is equal to NP. Thank you.